Welcome to the physics class for December the 17th. A couple of announcements before we get started. First off, don't forget to do the test rework. It is due tomorrow, Friday, at midnight. It's worth more than twice as much as a regular homework assignment is worth, so make sure you do it. And you can retake it as many times as you want until you get a perfect score, and I want everybody to get a perfect score. We will be taking a test very soon after we come back from the winter break. It won't be, immediately afterwards, but here's the plan. We're going to start chapter 11 today. And when we come back from the winter break, we will finish chapter 11 and then do a review and then take the test. So I would recommend that you go back and do any quiz retakes that you need to do. I've unlocked all of them except for the most recent one. I haven't had a chance to look at your results on that yet. And I need that feedback. That helps me know whether I need to spend a little longer reinforcing things or whether I can move on. So that feedback is important. So I'll look at that, and then later today or tomorrow, I will unlock that one too. So you can then retake all of the quizzes as many times as you want. Also, let's see, tutoring. So there will be tutoring this afternoon and also Friday at 11:30 and also Saturday at 11 and Saturday at 4. During the break, we're only going to do one tutoring session. That will be on Tuesday of next week. Other than that, no tutoring over the break. So you got lots of opportunities to get tutoring, guys. Please log on and participate in that. Okay, I'm thinking that's about it. Any questions before I start into last night's homework? Not seeing any, not hearing any. Okay, let's talk about last night's homework. Here are the answers to the ones that you haven't already looked up in the back of the book. As you can see, problems 14 and 26 are ones that I think I want to discuss. There's something important about each of those problems that I really want to emphasize. But I'm willing to listen if you guys want another one. So type in the chat box, if you could only see one problem worked through, which one would you want it to be? Not seeing too many inputs here, guys. Okay, 14 is getting a bunch of votes, 24, 28, 14 and 26. Okay, we'll tell you what, let's do 14 and 26, and then we'll see how it goes after that. Okay, 14 is very important. That's one where we're pushing on a car, but as the car moves, we find out that the amount of force we need in order to keep it moving decreases. So how do you calculate work if the force is not constant? Well, you do it the exact same way that we calculated impulse if the force wasn't constant. So let's just take a real quick sec and go and review how did we calculate impulse when the force wasn't constant. Okay, so let's start off by just reminding ourselves what is impulse. Okay, so impulse is defined as the amount of force that you're exerting times the amount of time over which it's being exerted. And if the force is not constant, how did we deal with that? Well, what we did was we said, in fact, let me change this from an arrow to an actual, change it to an equal sign, because that is actually correct to call it an equal sign. Okay, so this symbol right there, the elongated S, that looks like we've stretched it out there. So what we're going to do is we're going to integrate F delta T. And those of you who are not in calculus, you don't need to worry, because that is something you don't need to know how calculus in order to do. All you need to know is, what does it mean to integrate something? And hopefully you know the answer to that is, it means that you need to find the area under the curve. Under what curve? Well, if you look at the symbol here, whatever you see on the left side of the delta sign, that's your dependent variable. And whatever you see on the right side of the delta sign, that's your independent variable. So that means if we make a graph here, force is going to be in the y-axis, and time is going to be our independent variable. So in the problems we did a couple of weeks ago, if the force, say it increased for a while and then it holds constant for a while and then it all of a sudden stops, and we want to know what is the impulse, well, what did we do? We just found the area under that curve. And if it's a simple shape, you don't need to know calculus in order to do that. Now, if it's a complex shape or a curved shape, okay, then you need calculus. But all of the problems that we're going to do in this class are going to be simple shapes. So you don't need to know calculus in order to do it. You just need to know, what does this mean? All right. So it's going to be the exact same way with work. Work is defined as the force times delta x, not delta t this time, delta x. And if the force is not constant, we do the exact same thing we did before. We just do the integral of f delta x. All right. And so again, the dependent variable is the one on the left side of the delta sign. The dependent variable is the one on the left side. The independent variable is one on the right. So that means that the graph that we're going to find the area under is not f as a function of t, it's f as a function of x. All right. So we just need to graph the function and then find the area under the curve. Now in problem number 14 here, they say that it's a linear decrease. It starts off at 210. So when we first start pushing, we have to push with a force of 210 newtons. But as we push along, we find out that the force we need to exert decreases linearly until it gets to 40 newtons. And at that point, it stops. So what this means is find the area under that curve. And if you're thinking, well, I don't remember the formula for finding the area of a trapezoid, you don't need to know the formula for finding the area under a trapezoid. Break it up into two parts. Break it up into a rectangle. You know the area of a rectangle. And then a triangle. You know the area of a triangle. Okay. So the rectangle is base times height. So area equals that. So the base is whatever distance we pushed the thing over, and that was 15. And then the height is going to be 40. So 15 times 40, that will be the area of the rectangle. And then for the triangle, it's 1/2 base times height. The base is the same 15 as it was before. Now, some of you are going to say the height is 210, but I hope you realize that's not the case, because the triangle starts at 40 and goes up. So the height of our rectangle is going to be whatever 210 minus 40 is. All right, so we calculate that area, add the two of them together. And let me go back here to my previous page. Okay, so if we do it right, we should get 1,900 joules. All right. So this is something that everybody in the class needs to know. You don't need to know calculus. All you need to know is, what does it mean to take an integral? And it means find the area under the curve. Just be sure it's the right curve, because if it's the curve of f as a function of t, then the area under that is going to be the impulse. If it's the curve of f as a function of x, that's the one that's going to be work. All right, number 26. I'm hoping that some of you, when you did problem number 26, you looked at the picture and you said, hey, wait a minute, something's wrong here, because the book did in fact make a mistake. The artist who illustrated the book was not careful, and the author didn't notice the artist's mistake. So they have a picture. Where'd it go? Okay, so they have a picture that looks like this. There is a ceiling. There's a pulley hanging from the ceiling. Here is the object that we're trying to lift. And here is the rope that we're using to go wraps around the pulley and comes down here. Okay, so that's where we grab with our hand. So then, according to the written part of the problem, it says that we're going to grab here and we're going to pull down here. And we're going to pull the rope a distance of, I think it was 33 meters, was it? Yeah. Okay, so we pull the rope a distance of 33 meters. And they say that the box rises a distance of 16.5 meters. So at that point, you should have said, wait a minute, this doesn't add up, because the IMA of any device is given by taking the distance that your hand moves divided by the distance that the object moves. And so in this case, it's 33 divided by 16.5. So that means the IMA is 2. But if you look at the picture, you'll see, wait a minute, that doesn't make sense. Because the picture, so the pulley that they have here is the exact same pulley that I showed you the other day. Okay, it's just, there's just one wheel. Okay, so this thing's hanging from the ceiling. So when I pull here, the rope goes up on the other side. And remember how this works is that it's the same rope. So when I pull on the rope, the tension in the rope is the same anywhere in the rope. And if it goes over a pulley, as long as it's a frictionless pulley, then the tension on this side is going to be the same as the tension on that side. So when I pull down, that means the box is going to be pulled up with the exact same force that I pulled down with. Now the direction is going to be different, but if we don't worry about the direction, if we just worry about the magnitude of the force, okay, the force on the box is the same as the force of me pulling down, and so that means that the IMA is 1, which doesn't match at all. Okay, so looking at the picture, you'd say, well, the IMA is 1. But if you look at the information they give you in the text of the problem, it clearly says the IMA is 2. So what's the deal? Well, this was a mistake on the part of the book. The author did not draw a picture that matched the words, or the artist didn't draw it. Okay, so what do we do? Well, what I recommend we do is let's assume that it was the artist who made the mistake. And so what I'm going to do then is I'm going to say that this picture is, oops, that wasn't what I intended there. Okay, so what we're going to do is we're going to say this picture here is wrong. And we'll just say that instead of looking like that, it's some black box, some mysterious black box. And so we can't see inside the box, so we don't know what it looks like. We'll just trust the numbers that they gave us. And the numbers that they gave us say that our hand moved 33 meters, the box moved 16.5, so that means the IMA is definitely 2. No question about that. All right, now, they're not asking what the IMA is, at least not in part A. They're asking what the actual MA is. So how do you know what the actual MA of a machine is? Well, you can't get that just by looking at it. You have to measure the forces. And so in this case, they say that, well, actually, okay, so first let's finish the formula. So the actual MA is the output force, which your book likes to call the FR, divided by the force that you're exerting, which is I like to call it the input force, but your book likes to call it FE. All right, and so they tell you how hard you're pulling. They say that you are pulling with 129 newtons. Now, they don't tell you a number for what the output force is, but they do give you the information you need in order to calculate it. If we were to do a free body diagram on the box, we got mg going down, and then the force of the rope pulling up, okay? And so that's the output force from the machine. That's what's pulling the box up. So whatever the output force of the machine is, it must be equal to mg. And they tell us what m is. They tell us that m is 24 kilograms. And we know what planet we're on, so we know what g is. Or at least if they don't tell you that otherwise, you can safely assume that it's Earth. Okay, so what we need to do then is we need to take whatever 24 times 9.8 is, and then divide that by 129. So 24 times 9.8, divide that by 129. And so that tells us that our actual MA is 1.8 if I round off for 2 sig figs. Okay, so there's the answer for part A. And then for part B, they want to know what's the efficiency of the machine. Well, efficiency is defined as the actual MA divided by the ideal maximum possible MA if there were no friction. So the actual MA is 1.8. The ideal maximum possible is 2. And so whatever 1.8 divided by 2 is, okay, so that's 0.91. Now if I use the rounded off 1.8, I get 0.9. But if I use the 1.8 with a couple extra sig figs, I get 0.91. Okay, but when we're talking about efficiency, your book always expresses it as a percentage, which is the most common way to do it. I mean, not everybody. There are people out there who will leave it as a decimal 0.91, but most of the people will put it as a percentage, and your book does it that way. So that's the way that you should do it too. Okay, so that means it's 91% efficient. That's the answer that you should write down. Okay, all right. I hope that helps things make sense there. Any questions about what I just did? Not seeing any or hearing any. Okay, so if you have a couple questions about some of the other problems, please hold them until the end of the class. I want to make sure we have enough time to talk about the new stuff for today. Okay, but before we jump into chapter 11, I do want to finish up a couple things about machines that I hoped that you would get from looking at the extra credit that I talked about. Oh, yeah, you guys, this is the B-Day class. I forgot to tell you about the extra credit last time, but I did send you the email. So I hope that you read the email. Okay, so if you look on Canvas where I've got the extra credit problems, then you'll see that there's a couple videos that I added on very recently that weren't there before that talk about when I was out on the ocean and I needed to pull on the sail with more force than I could humanly do. And so the question that you guys had to answer was, how do I do it, and what is the IMA of the way that I did it? Okay, so if you responded to my email and submitted an answer to that, I will give you extra credit. But right now, I'm going to go over the answer to it. So from this point on, it's no longer going to be extra credit. And that's the way it works with all of those videos on my extra credit. You have to answer them before we talk about them in class if you want extra credit. Otherwise, it's not deserving of extra credit. Okay, so what I did in the video there was I showed you a pulley that I was using. And so let's take a minute and let's look at all the different types of pulleys that are out there. In fact, let me stop for just a sec. You guys have heard me say many times, the best way to learn physics is to go sailing. And you probably thought I was joking, but I wasn't. I am absolutely serious when I say that, because if you're a sailor, you need to know vectors, right? I mean, your life could literally depend on you being able to add vectors. But you also need to know how to work with machines and how to calculate your force multipliers. The pictures that you're seeing right now, these are pictures that were taken from a test that I had to take several years ago when I got my captain's license, because I am a licensed sea captain. In fact, if you want to call me Captain Doug, you could, because legally I am a sea captain. And I had to take a test in order to get that license. And some of the problems on the test had to do with pulleys, because sailors need to know pulleys. And so what you see here are a bunch of different pulleys. And the ones that you see on the left right here, these two pulleys, this one's called a whip rigging and this one's called a runner rigging. It's the exact same pulley that I showed you last time. It's just a single wheel with the rope going over it. And right here, single wheel with the rope going over it. The difference is how you rig it up. And when I say rig, I mean how you run the ropes through it. Okay. So if you rig it up in what a sailor calls the whip configuration, you've got an IMA of 1. Now, actually, it's an IMA of -1, but sailors and many other people who work with pulleys all the time, they don't usually worry about the minus. They just take the absolute value of the IMA. So if you have a single wheel pulley, rig it up like this, you get an IMA of 1. But that exact same single wheel pulley, if you rig it up differently, you can get an IMA of 2. Okay, and then this over here, this is what sailors call a gun tackle. And what you do here is you have 2 of these single wheel pulleys. And if you rig them up like this, you get an IMA of 2. But if you rig them up like this, you get an IMA of 3. And so, I mean, this is something you need to understand if you're going to be a sailor. Okay, this over here, let me try that again. This over here is what sailors call a single luff tackle, and you can get an IMA of 3, or if you rig it differently, you can get an IMA of 4. And then the last one that I'm going to talk about today, this is called a two-fold purchase system. This one, you've got a double pulley like over here that you had it over, same over here. This is a block that has 2 wheels in it. Okay, so sometimes it's called a block and tackle. Okay, so if you rig it up like this, you can get an IMA of 4. You rig it up like this, you get an IMA of 5. So in the extra credit video that I showed on Canvas, I showed you a picture of the pulley that I was using that was connected to the sail, and I asked you to calculate what the IMA of it was. So this is something you need to know, because when we take the test right after the break, it's entirely possible that I might show you a picture of a pulley of some sort, and I might ask you to calculate the IMA of the pulley just by looking at it. Wink, wink, nudge, nudge. Okay, so let's talk about how to do that. Let's pick one of these just at random here, and let's see, how do you calculate the IMA of a pulley? So let's suppose that I take a single luff tackle and I rig it up like this. And let's suppose that that's covered up, so we don't know what the IMA of it is. We need to figure out what the IMA is just by looking at the picture, because it is possible to do. So the question then is, how do you do it? Well, what you do is you draw a dotted line around the part of the pulley that is connected to the load, the thing that you're trying to move. So you can think of it as we're going to define our system to be that block that is attached to the load. And then what we do is we just count the ropes. So you can see that coming in here, I've got 1 rope, 2 ropes, 3 ropes, 4 ropes. Now, don't forget, it's not 4 different ropes. It's the same rope, just wrapped around the wheels. Now, as long as those wheels have no friction, the tension is going to be the same, because when you have a rope and you stretch a rope, the tension in the rope is the same all throughout the rope, even if it goes around a pulley, as long as the pulley is frictionless. Now, if the pulley is not frictionless, then every time you go around the pulley, you're going to lose a little bit of tension. But if we're calculating IMAs, that by definition means we're assuming frictionless pulleys. Okay, so what we've got is we've got 4 force vectors pulling upward, and each of those force vectors is equal to the tension in the rope. So that means our total upward force is 4 times T, and T is equal to the force that we are pulling with. So our effort force, that's what's pulling on the rope. So that means our upward force here is 4 times whatever our effort force was. And when now we've only got 1 rope coming out of the pulley on the bottom, and this guy on the bottom must be equal to what's on the top. So that means that our output force, FR, okay, must be equal to 4T, which means it's equal to 4E, so, or 4 times the effort force. Okay, so just by looking at the picture, we can see that the IMA of this single luff tackle is 4, as long as we rig it the way that we've rigged it here. If, on the other hand, we had rigged it differently, that exact same hardware, but if we had rigged it like this, now, if I draw the box here, this rope does not count, because this rope does not connect to the lower wheel there. The only ropes that are connected to the lower wheel are these. Count the ropes, I see 3 ropes. That means my IMA is 3. Okay, so make sure you know how to do this because it might be a question on our next test. Wink, wink, nudge, nudge. Okay. All right, so that was only part of the extra credit video that I showed you. The other part said that, okay, let's suppose that the sail is so big, which by the way, that it's so big that, and the wind is so strong that if I pull on the sail, even using that pulley, it's still not enough of a force multiplier for me to pull the sail in. And that actually is the case because on a big sailboat, the sail is really big and the wind can often be so strong that even with the pulley, I still can't do it. So if you watch the video, which by the way, if you haven't watched it yet, I highly recommend you go on and watch it. Okay. What you'll see is that I looked around the boat and I said, oh, well, I've got this other machine sitting right here. Maybe I can use this other machine to pull. And so what we had to do is we had to calculate what's the IMA of this other machine. And so the way that we do that, come on, it doesn't want to let me write on the screen. Okay, so we draw a line through the center of the thing. And then we look to see what is the distance to the handle, because that's where we're going to be exerting our input force. So your book likes to call that DE. And then you see that we've got this rope coming in here and the rope wraps around the drum. And by the way, that's what this is called. This is called a drum. And the drum has these rough markings on it so that gives it lots of friction. So what happens then is that when I rotate the handle, then the drum is going to rotate and it behaves exactly like a wheel and axle, which is one of the simple machines that your book talked about. Okay, so if I want to know what the IMA of this is, all I have to do is find out, okay, what's the distance from the center to my handle, and then what's the distance from the center to where the rope is wrapped, and so let's call that DR. And so the IMA then is going to equal DE over DR. Now in the video, I actually measured the handle and everything, but for today's purposes, let's just make up some numbers. Let's assume that DE is 12 inches and DR is 3 inches. And so that gives you an IMA of 4. Okay. All right. So let's suppose now that here I am out on the ocean and I need to pull the sail in and I can't pull hard enough. So if I use this winch here, I can get an IMA of 4. If I use the pulley system, if I look at if these are the available pulleys that I have to use, even if I use the twofold purchase rigged up this way, the IMA that I get is 5. So neither one of those by themselves is going to do the job for me because I need an IMA that's more than that. So what can I do? Well, if you watch the video, then you find out that what I did was I combined the two of them together to create what's called a compound machine. And your book talked about it, and I trust that you read the book before you did the homework, right? Okay, so the idea with a compound machine is you take one machine and then you take the input rope from that machine and hook it up so that it's the output rope from the other machine. So if the winch here gives us an IMA of 4, so that means it's a force multiplier of 4. And if we're using a pulley system that is rigged in such a way, so it gives us an IMA of 5. So then what is the total IMA of the two of them if I use them together as a compound machine? So what do you think? What is the total IMA? I mean, there's a couple possibilities. One is that it could be 5 plus 4 to give me 9. Or the other one is it could be 5 times 4 to give me 20. So what do you guys think? I'd like everybody to vote. What do you think is the total IMA of the combined compound machine? Do you think, how many of you vote for 9? How many of you vote for 20? I want to see everybody voting here. And if you want to vote privately, that would be okay. Public is okay too. All right, it looks like the overwhelming majority of you are saying that you want it to be 20. And a few of you who sent me a message privately said that it's 9, but most of you are saying 20. And Max is backing up his number with some logic. He's saying that both machines are multipliers, and that's exactly the right way to think about it. Okay. So this machine over here, it will give you 5 times whatever the output is of this machine, but this machine is 4 times that. So this is five times that, not 5 plus it. So the answer is 20. Okay, so what that means then is if I were to grab hold of this handle and I pull on this handle with a force of 100 newtons, the force that comes out of the compound machine, whoops, let me fix that. The force that comes out of that compound machine is going to be 20 times that. So I'm going to get an output force of 2,000 newtons, which will definitely be enough to pull in that sail, even if the wind is blowing really, really hard, and even if the sail is really, really big. Okay. So now you can see why I say the best way to learn physics is to go sailing. I'm not joking. It really is true. Okay. So with that being said, let me go ahead and jump into tonight's homework, or at least tonight's content. So let me share the screen with you here. All right, so as I said a few minutes ago, we're going to start into chapter 11 today, and we're going to learn about other types of energy, not just kinetic, but there are other types of energy. And it turns out that energy is conserved just like momentum was. So you remember when we were doing collisions just last week, we said that the total momentum before the crash, and let's write it like this. So the total momentum before the crash had to be equal to what you get if you add up all of the total momentum after the crash. Now, that doesn't mean that each individual object has the same momentum after the crash as it did before. What happens is one object will give some of its momentum to the other object, okay? But the total before has to equal the total after. Well, it works the same way with energy. If you were to calculate how much energy a system of multiple objects, or maybe the same object, doesn't matter. If you look at some situation, you calculate how much energy does it have before some event happens, and you compare that with how much energy it has after the event happens, you'll find out that the total is the same. So it works just like that. So I'm going to say sigma E before the event has to equal sigma E after the event. Now, the thing is that the form of the energy might change. Like, for instance, before the event happens, all of your energy might be kinetic energy. And then after the event happens, some of that kinetic energy might have been transformed into other types of energy, but the total will be the same. Now, up until now, we really haven't talked about other types of energies. I have told you that there are other types, but we didn't really go into them. So what we need to do today is we need to learn about at least some of those other types of energies. All right, so the first type of energy that we're going to learn about is called gravitational potential energy. So G stands for gravitational, P stands for potential, E stands for energy. And quite often, people they leave off the G. Usually they just say PE, which is a little bit of a problem because there are other types of potential energy. There's also like chemical potential energy. If you've got a bunch of chemicals sitting around, they have the potential to do work. If you mix them together and they react, those reacting chemicals can give you energy. So there's chemical potential energy, there's electrical potential energy. Okay, if I take a battery, there is stuff going on inside this battery that creates something called voltage, which we're going to learn about later in the year. that I could use to run a motor or something. So I have electrical potential energy, and I have thermal energy. I have all sorts of different energies, but let's focus in on gravitational potential energy. And I'm going to be lazy because your book does it. I'm going to leave off the G. And so let's see how does that work. Okay, so the one way I like to think about it is this. If I were to take this book and I throw this book at your head, okay, when that book hits your head, it can do a lot of work on your head. So we know that the moving book has energy. And in fact, we know how to calculate how much energy it has. We know the energy of this moving book as it approaches my head here is 1/2 times the mass of the book times the velocity of the book squared. Okay, so moving book has energy. It can do some serious work on my head if it hits my head. Well, how about if we do this? Let's suppose that I take this book and I start off, it's sitting on my head. So if I take my hands off it, okay, it doesn't do any work on my head because it started off there. But if I lift it up, okay, now if I remove my hands quickly, it's going to come down and bonk me on the head, and it can do some serious work on my head. So this book that is poised up above my head, it has the potential to do work on my head, even though it's not moving. So that means it has energy. Okay, so then the question becomes, how much energy does it have? Well, let's open up a whiteboard and let's see if we can figure that out. Okay, so here is the ground level, and here is some object sitting on the ground level. And so the height of the box of the object above the ground is 0. So it's like the book when it's sitting on my head. If we take our hands off the object, it's not going to do any work to the ground. So it has no potential energy at that point. But what we're going to do then is we're going to lift it up. So now the box is sitting here at some height that is not 0. Now it has the potential to do work. If we let go of that box, it's going to fall down and it's going to hit that ground. And if my toe was in between that box and the ground, that box is going to do some serious work on my toe. So it has the ability to do work. How do we calculate how much energy it has? Well, the easy way to do that is just calculate how much work did we have to do when we lifted the box up. So let's do a free body diagram. Here's the box. We've got mg going down. This is the force that we had to exert when we lifted up the box. And we know that work equals force times delta x, and also times the cosine of theta, except this time we don't need to worry about cosine theta because our force is going up vertically. And when we lifted the box up vertically. So there's our delta x vector. Okay, and so you can see they're parallel. So theta equals 0, the cosine of theta equals 1. So we don't need this guy. He doesn't really serve any purpose. All right, so the work that we do in lifting the box up, well, F is just equal to mg. The distance that we lifted it, well, that's just h. So the work that we did then is equal to mgh. That, by definition, is the gravitational potential energy, which your book usually just calls PE. So if you see the letters PE, you can safely assume that they're talking about gravitational potential energy and not chemical potential or electrical potential or elastic potential. Like, you know, if you stretch rubber band, that stretched rubber band has energy, right? We call that elastic potential energy. So if they just call it PE, you can safely assume what they mean is gravitational potential energy. And so this is how you calculate it right there, just mgh. So that's pretty straightforward. Okay, so let's do a couple of problems like you will see in your homework tonight. Let's suppose that we have a ramp, and we have a box sitting on the ramp, and the box is sitting at some height above the ground. Let's call it h, and let's say they give you a number. You know, let's say it's 12 meters. And here is some angle here. And maybe they'll give you an angle for it and or a number for it, and maybe they won't. It turns out that you're not going to need to know the angle. Okay, so let's say that the initial velocity of the box is 0. And so it's sitting at some height h above the ground. And what we're going to do is we're going to let go of the box, and it's going to start sliding down. And we want to know what is the velocity of the box right in that fraction of an instant right before it reaches the ground. This is what we want to know. Okay. Now, if you were asked to do this the old way, you would have to know what theta is. So let's just very briefly talk about how we would do it if we did this the way that we learned a couple months ago. So we would do a free body diagram. So we got mg going down, we got the normal force going up, and then we would say, well, we need to break it up into its components. Mg is the funky one. Okay, so this one right here, mg sine theta, that is the force that pulls it down the ramp. Now, if we assume there's no friction, then there is not going to be a friction force opposing it. So let's get rid of that. So the only force that's pulling it down the ramp is mg sine theta. That's equal to mass times acceleration. Masses cancel. So the acceleration then equals this. And then we can use the equations of motion, the ones that I like to call the Dr. Seuss equations, and we can apply those. I'm not going to talk about how to do them, but basically at the end of all those steps, we could figure out what V final is. I propose to you that there's an easier way. Now that we know about energy, there's an easier way to do that. Okay, so what we're going to do is, let me just do this real quick over here. Okay, so initial velocity is 0. Final velocity is what we want to know. And it starts off at some distance h above the ground. So we're going to say, well, conservation of energy tells us that if we add up all of the energy before the event happens, we have to get the same number that we would get if we were to add up all of the energy after the event happens. All right, so what have we got before the event happens? Well, first off, what I like to do is I like to just make a list of all the energies that might possibly be there. So I'm going to say potential energy, and by that I mean gravitational potential energy. That's one possibility. And then kinetic energy is something we need to think about. And then we should also just think about there might be other forms there. There might be electricity or chemical or something, okay? And then that has to equal what we get after the thing has happened. So again, there's potential energy, and let's put an A here. Let's put a B on all of these guys. That stands for before. And then there might be, oops, that's not an equal sign. Sorry, that should be a plus sign. Okay, and there might be kinetic energy afterwards. And let's put in other, because there might be some springs or some batteries or whatever. Okay, all right, so I recommend you start off this way. And now we look at the picture we've been given. Okay, so we start off, the thing is at some height h above the ground. So we definitely do have some potential energy. So we've got mgh. The initial velocity is 0, so that means we do not have any kinetic energy. There are no batteries or anything. And also, by the way, there's no friction. So that's something you need to worry about, because when you have friction, then you have that gets into heat. In fact, let's take a minute. So if you take your hands and you rub them together like that, the friction of your hands rubbing against each other produces heat. So that's thermal energy, which is something we're going to talk about in just a very few minutes. But if there's no friction, then we don't have that. Okay, so the only energy we have before is just potential, nothing else. How about afterwards? So if the box is down here, if it's at that infinitesimal bit right before it hits the ground, then h equals 0 at that point. So that means we don't have any potential energy. Now we do have some kinetic energy, so we got 1/2 m times v final squared. And then again, you need to think about, is there other? So has there been any friction that might convert energy into thermal? Are there any batteries? But in this case, there are not. Okay, so there you go. mgh equals 1/2 mv squared. From this point on, it's no longer a physics problem. Now it's just a math problem, and you're good at math, right? So you notice that both sides have an m in it. So if g is a known number, and if h is a known number, then I'm thinking we can figure out what vf is very, very easily. So let's multiply both sides by 2, take the square root of both sides, and so the square root of 2 times g times h, that is v final. And that is the exact same answer that we would have gotten had we done it the old way. And by the way, for the old way, we would have needed to know what theta was. And then you notice the way that we did it here, we didn't need to know what theta was. So it doesn't matter if that's a steep ramp, or maybe it's a shallow ramp, or maybe there's no ramp at all. Okay, maybe what we did was we just took a box and we held the box at some height h above the ground, and we just let the box fall. Okay, so when this black box that you see right here, when it is just infinitesimally above the ground, the velocity of that black box and the velocity of this red box will be the same if there's no friction. Big if. Okay. And it was a whole lot easier to calculate using conservation of energy than it was the old way using all of the Dr. Seuss equations. Now, I highly recommend that you go back and solve it the old way and just convince yourself that it's true. It does work out, which is kind of nice. Okay, now, what do you do if there is friction? Because there might be some friction in some of the problems that you're going to do tonight. Okay, so how do you handle it if there is friction? All right, well, let's take a simple case. Let's assume that we've got a horizontal floor. We've got a box that is moving with some initial velocity that is not 0, and there is friction. And so what's going to happen to this sliding box? Well, the friction is going to exert a force on it. So as it's sliding along, there's going to be a friction force that's going to cause it to slow down. And so what's going to happen then is after it's gone some distance here, it's going to go slower and slower, and then finally it's going to come to a stop. And so what you might be asked to do in the homework is that you might be asked to calculate what is the distance that it slides. And now if they were to do that, they would tell you what the mass of the box is. So, maybe it's 12 kilograms. I'm just making stuff up here. And they'd need to tell you what the initial velocity of the box is. Let's say it's 20 meters per second. Okay, and they would need to tell you what the coefficient of friction is. So let's say mu equals, 0.4. Just so all of these are known numbers. So what you need to do is you need to calculate how far is the box going to slide. Okay. Now, again, this is a problem that we could solve the old way. And I'm not going to completely solve it the old way. Let me just briefly tell you how you would do it. Okay. Or actually, you should know. Maybe I should ask you to tell me how to do it, but because we're short on time, I won't do that. So what you're going to do is you're going to do a free body diagram, and we've already pretty much done it here. So this was the only force that's acting on the box in the horizontal direction is the force of friction. Now we do have mg going down, and we do have the normal force going up. Okay, and there is no force in the forward direction. I mean, there was initially to get the box moving, but once the box starts moving, we stopped pushing on the box and it's just sliding along. So in the horizontal direction, the only force acting is the friction force. So when we do sigma F equals ma, well, and we'll do it in the x direction, friction is the only one. So that means the force of friction is equal to mass times acceleration. What's the force of friction? Well, that's mu times the normal force. What's the normal force? Well, the normal force is mg if you're sitting on horizontal ground. If you're on a ramp, it's mg sine theta, but if you're on horizontal ground, or mg cos theta. But if you're on horizontal ground, cosine theta is 0, which is 1. Okay, so mu times m times g equals m times a. Cancel out the m's, and you know what a is. And so then you go and you look at your Dr. Seuss equations, and you look at, v final squared equals v initial squared plus 2a delta x, and you say, okay, we can solve this. Or you could solve it the new way, which is way easier. Okay, so let's solve it the new way. What we're going to do is we're going to say, well, the law of conservation of energy says that if we add up all the energy before some event happens, it has to be equal what we get if we add up all the energy after the event happens. Okay, so what have we got before? So so this is the before case. Well, the box is sliding along, and now everything is happening at ground level. So our height is 0. So we have no potential energy to worry about. All we have is kinetic energy. All right, so what do we got before? Just 1/2 mv squared. That's the only thing. What have we got afterwards? Well, it's still at ground level, so there's no potential energy. It has come to a stop, so there's no kinetic energy. So we look at it and say, well, it looks like we just violated the laws of physics. We had some energy before. We don't have any energy now. It looks like we violated the law of conservation of energy. Well, no, because we forgot about other. Okay, don't forget there are other forms of energy. Right? So where did the energy go? Well, rub your hands together and you'll find out where it went. Okay, whenever you have friction, what you're doing is you're converting this mechanical moving energy, you're converting that into thermal energy. Your hands get really warm when you do that. Okay, so the work that is done by friction, it gets converted into thermal energy. Okay, so this is going to be now thermal energy, which is the work done, and I shouldn't say by friction, I should say the work done against friction. Okay, all right. So what we need to do is we need to say, okay, as the box was sliding to the right, my picture here is getting pretty cluttered up. Let me get a new picture. So as the box was sliding along, it was working against friction. And so friction was exerting a force on the box. Newton's third law says there's always an equal and opposite reaction force. So the box was exerting a force on the floor that was equal to that. And so the box was doing work on the floor. And work equals force times distance times the cosine of theta, but theta is 0, so we can leave that out. All right, so the force that the box is doing is equal to and opposite of the force of friction. And the force of friction is mu times the normal force. Okay, the distance, well, that's how far the box slides, and that's what we're trying to find out. Okay, and so that is the thermal energy. So all of that work gets converted into thermal energy. So on the previous page here, where we said that before the thing encountered the friction, it had kinetic energy of 1/2 mv squared. Afterwards, all of that energy has been converted to heat. And so what we have then is we have 1/2 mv squared. That's the energy before. Oops, that's that 2 there should be a squared. Okay, that is the work done by friction, which is force times distance, which is that. So that's equal to mu mg delta x. And from this point on, it's no longer a physics problem. Now it's just a math problem, and you're going to math, right? So notice that the mass of the box cancels out. And so if we multiply both sides by 2 and take the square root, we find, and remember this v here is the initial velocity. Okay. Let's see, we're trying to solve for delta x, not the initial. Okay, so what we're going to do is we're going to divide by mu g. Okay, so what we get then is v squared over 2 mu g, that equals delta x. And there you go. We know what v initial was, we know what mu is, we know what planet we're on, so we know what g is. That turned out to be a heck of a lot easier than it would have been had we done it the old way, where we used Newton's second law to figure out what the acceleration was, and then we go and we figure out which of the equations of motion to use. Okay, this new way turns out to be a whole lot easier. And so you're going to find that that's going to be the case for many, if not all of the homework problems that you're going to have tonight, is that every one of them, or at least most of them, could have been done the old way, but it's going to be much easier to do if you do it the new way. So Lucas is saying, what happened to the 1/2? I'm pretty sure it's still there. Yeah, there it is right there. There's the 2 right there. Okay, that's the 1/2. I didn't mess that up. You were hoping that you can get me to wear the wig one last time before the year ended, weren't you? Haha, no, no wig. Okay, so I think you are well positioned now to do the homework. I realize I hit you with a lot of stuff really fast and didn't give you time to ask questions. Anybody have questions you want to ask? All right, so I guess you probably want to know what the homework is. Now you, of course, could just look on Canvas because it's on Canvas. So here it is, problems 1 through 8, and then also problems 15 through 18, this from chapter 11, obviously. Read the book before you do the homework problems. Do not assume that I'm spoon feeding all the information to you need. Okay, there's stuff in the book that you need to know. And then don't forget to take the daily quiz. And so now the daily quiz isn't due till the next time we meet. So I'm going to have to keep it at you're only allowed 2 tries. And then after the winter break, I'll look at your results and then I'll unlock it then. So other than quiz 10B, all of the other quizzes, 10A, 9A, 9B, those are all now unlocked. So you can retake those as many times as you want. Okay, I'm thinking we're good. So if you want to head out, remember, class is not over. We still have 20 minutes left. So you should use that time to read the book and get started working on the homework. So if you're good, you can go ahead and type bye into the chat box and head out. If you are waiting for me to turn off the recording so that you could ask a question without it being recorded, I will do that now.